Okay, welcome to lecture here. We're continuing on in chapter 9, talking about stoichiometry here. All right, so last time we started talking about stoichiometry, and again, a reminder that basically stoichiometry is kind of combining a couple of topics that we talked about previously, balancing equations, converting grams to moles, and basically using both of those things to figure out things based off of the equation, how much product we should form, if we know how much product we could form, how much reactants we started with. And really what stoichiometry is, as we talked about last time, is really nothing more than sort of conversion factors. And again, instead of sort of getting those conversion factors from a table or anything like that, where we essentially get them from is the actual balanced equation. So definitely always important to start with a balanced equation when we're doing stoichiometry. The reason for that is we use what's known as the mole-to-mole relationship when we do stoichiometry, and that does come from the balanced equation. And when we do basic stoichiometry problems, which are essentially like the ones that we talked about last time, there's really obviously kind of 4 steps that we usually do. And we talked about those steps. We sort of solve those steps. And the first step is really, as I mentioned, everything really does start with that balanced equation. So you always want to make sure you have that. Otherwise, none of your calculations are going to be correct. None of your mole-to-mole relationships will be correct. And then in a basic stoichiometry problem, they usually will just give you one piece of information. And whatever they give you in terms of that information, you want to convert to moles. So again, if it's already in moles, you don't have to do that. If it's in some other unit, you do need to do that. The way that we typically can do that is by converting grams to moles a lot of times. So a lot of times it's a grams to moles type of conversion, and that usually requires the molar mass to do that. Now, the third sort of step is actually the stoichiometry step. That's the mole-to-mole relationship. And that mole-to-mole relationship, again, comes from the balance equation. So, for example, this one that we're looking at here, we could use just the coefficients, and we basically say for every 2 moles of A, we can react it with 1 mole of B. We could also say for every 2 moles of A we throw in there, we can get out 2 moles of C. We could also say for every 1 mole of B we put in there, we could get out 2 moles of C. So these are sort of equalities, and as we talked about last time, they're not equal in terms of, obviously 2 and 1 doesn't equal each other, but they're equal in terms of sort of proportion. So in this particular reaction, we need these sort of proportions of each of these guys to come together to produce a certain amount of product. And from each of these, we really can write 2 conversion factors as we did last time. And that really is sort of the stoichiometry part. And lastly, sort of the 4th step is to take those moles, because as soon as you do step number 3 here, you're always going to be in units of moles. So the next step is to take those moles if you need to. You don't always have to. But if you need to, and convert it to some other unit, again, very common to convert it back into grams. So a lot of times on the back end here of the calculation, we also will be using molar mass as sort of a conversion factor from the periodic table. So as we talked about before, it always needs to be that mole-to-mole relationship that comes from the balanced equations. And as this question here asks, that's why we really don't use grams to grams, so we do need to convert it into moles. The reason we don't use gram to gram sort of relationship, again, is the molar mass of everybody is different. So when we say we have 1 mole of carbon, for example, that is 12.01 grams. We have 1 mole of oxygen, that's 16 grams. But using that mole-to-mole relationship sort of gives it a standardized way of relating things to each other. Again, we can't do gram to gram because those grams are different for each of those things. And I think that's actually what this sort of says here in terms of those 4 steps. And again, no matter how sort of difficult a problem may look, how crazy a calculation may look, or anything like that. It really is in a basic problem, these 4 steps. You know, start at the first one and keep going to each of the steps. Anything that's done for you obviously can, you know, continue on past that step to the next one. Any questions on that stuff that we were talking about last time? So in addition, last time we sort of did jump into kind of going from moles back to grams, kind of doing that 4th step. And again, this is just a reminder that, you know, when you get to that sort of 4th step, if you need to, there's many units that you could do. You're in moles, so if you want to know something about atoms or molecules, you obviously could use Avogadro's number to do that, which would be going obviously, say, from moles to those guys, using our Avogadro's number, which should be obviously 10 to the 23 up on top. Again, most common though, usually in stoichiometry problems, is you want to get the grams, and again, that molar mass from the periodic table, which is really sort of a conversion factor as well, which is how many grams there are per mole, allows us to go from moles into some unit like grams. So here, for example, if we want to kind of put these together, we'll just kind of go through these steps here and sort of work our way through it. So we want to make sure that we are starting with a balanced equation. So in this particular case, it's not balanced. We might need a perhaps a 2 here, maybe a 3 there, and maybe a 4 there, and that should balance it up, I think, right? So we want to make sure it's balanced. Just to make sure we got 4 chromiums on each side and 6 oxygens on each side. So step number 2 is to take whatever they gave us. So in this particular case, they gave us 15 grams of solid chromium. So that's what we would start with. And we do want to convert that into moles. So we would go to the periodic table. We would look up chromium, and it's about 52 grams per mole from the periodic table. Again, that's chromium, right? And if we do that, we would take 15 divided by 52, gets us something like 0.28846. Again, I'm just going to take it to a few digits there. I'm going to round everything at the end. At this point, we've now got it to moles of chromium, but we're not really interested in chromium. We're actually interested in the chromium 3 oxide. So this is our 3rd step, which is our mole to mole relationship. So that is our chromium here, which is what they gave us. We're interested in our chromium 3 oxide. Again, from the balanced equation, we can see that there are 4 moles of chromium for every 2 moles of Cr2O3. That gives us, as we talked about last time, 2 different sort of conversion factors that potentially we could use. One that looks like this, and basically the other is the opposite of it, where we have our 2 moles of the Cr2O3 over our 4 moles of chromium. Here, since we are starting with our chromium, we want to get rid of that. So in this particular case, we would use the top conversion factor. That's going to get rid of it for us. Going to put the chromium on the bottom. And our 2 moles of Cr2O3 up on top. Moles of chromium are going to cancel each other out. So we're going to multiply by 2, divide by 4. Going to give us something like 0.1442 moles of Cr2O3. Again, that mole to mole relationship is nothing more than, again, the balance coefficients. At this point, we do need to do step number 4 here because we're looking for units of grams. If we just wanted moles, we pretty much would be done at this point, and we could put a box around it. So the last step that we need to do is that 4th step. We again need to go to the periodic table and get the molar mass. So also a really important thing. You do need to show it, so you do need to show all the work. Again, this is the same as a 1 to 2. It'll come out the same, obviously. But you do need to show this. You probably should show it with the correct sort of coefficients, even though you could technically reduce it down and stuff like that. So, so part of the work, you definitely want to make sure that you show all the steps. Again, you don't have to do it kind of step by step like I'm doing. You could do it all in one sort of calculation like we talked about last time. But you do need to have sort of all these parts sort of present. When we do the molar mass of Cr2O3, which is really where we're at this point, a couple of things that people also sometimes mess up on when they go to do the molar mass, and especially in stoichiometry problems, they see this 2 in front here, and they decide they should double the molar mass. So a reminder that if you're going to get the molar mass of something like this, you should do it just based on the formula, regardless of the coefficient that's there. We took care of the coefficient here, so you don't want to do it again on the second part of it. So that means that we would have 2 chromiums at 52 grams. We have 3 oxygens at 16 grams from the periodic table. And adding that together there would get us 152 grams per mole. And again, that's going to be our 4th step here. We're going to continue on with our number. And again, if you are doing it in steps like I did here, you really don't want to round too much until the very end. I personally haven't really cleared my calculator. I'm just continuing on with the whole number, my calculator. And again, try not to round too much along the way here. And if we multiply that by 152, we end up with something like 23,104 grams of Cr2O3. Any questions on that so far? Again, that is not really technically our final answer in this particular case. We should end up with make sure I typed in everything right here. Divided by 52, right? Times 2 divided by 4. 0.144. Go, and that is 152. I think I did punch it in wrong, so let me just double check that there. All right, try that again. All right, so if you actually punch it in right here on your calculator, apparently, one more time here, 1.442 times 152. There we go. Gives you actually 21.9. Sorry about that. 21.9. Well, that didn't seem too right. Grams of Cr2O3. In terms of significant figures, really, you know, probably you should go back to this very first number as it's the only number that was given to us. This has 3 significant figures. And here, obviously, we end up with also 3 sig figs. This, as we talked about last time, since it is a product, this would be what is referred to as the theoretical yield. Any questions on any of those steps? Again, you can see hopefully it's the same 4 steps. Like I said before, you could just do this all in one big calculation and get to the end is perfectly fine. If you do it sort of step by step like I did here, again, don't round it till the very end and probably punch it in your calculator better than I did there, I suppose. Any questions on any of those steps there? Okay, so we just kind of go through this. It's everything we just did. All right, so why don't you take a second here and give this one a go. Tin 2 fluoride is added to how many grams of tin 2 fluoride can be made from 55 grams of hydrogen fluoride. Again, if we look at some numbers that we probably need here, we got 10, yeah, there, 118.7. Hydrogen 1.008, and fluorine 19 grams per mole. See what you come up with real quick. Okay, so let's take a look, see how we're doing. So again, you want to start with the same steps. So I don't see any coefficients in this equation, so probably not balanced. And it's not, so hopefully you found you just need to put like 2 right about there to balance it. So that's the first step you want to do. Again, here they gave us really just one number, which is 55 grams of HF. We then want to convert that into moles. So we would need the molar mass of HF. And again, the molar mass of HF is basically 1 hydrogen. So that's 1.008 and 1 fluorine, which is 19. So that's going to give us a molar mass of about 2001 grams per mole. So again, we would use that to convert our grams into moles. And again, grams would go on the bottom here. Our grams will cancel. That's going to give us 55 divided by 2001. Going to get us something like, again, I'm just going to take it to a few digits here, 2.7486 moles of HF. At this point, we're ready to do sort of the stoichiometry part, which is step 3. We want to find the two things we're interested in. So obviously they gave us this guy, which is 2 moles from the coefficient. And we're looking for this guy here. So that tells us that for every 2 moles of HF, we get out 1 mole of our SnF2. So we're going to use that again here in step number 3 to go from our moles of what we don't want and do the stoichiometry part here. Again, to get rid of our HF, we're going to put it on the bottom. So that tells us that there are 2 moles of HF for every 1 mole of our SnF2. Moles of our HF are going to cancel. Basically, again, if we get a number at this point, you got something like 1.374 moles of our SnF2. Again, here we are looking for grams. So we do need to do step number 4, and that would be using the molar mass. So again, at this point, we've got to remember that we did convert into SnF2, so we want to get the molar mass of that guy, and that basically is what we got there. We got 1 SN at 118.7 plus our 2 fluorines, and that's going to give us something like 156.7 grams per mole. That will be our last little guy here, 156.7 grams up on top, moles on the bottom, so everything cancels out. Moles will cancel, and we will end up with 156.7. I'll try to punch it in the right way. Going to give us something in the ballpark of about 215 grams of SnF2. Again, here, in terms of sig figs, going back to our original number, which is usually a pretty safe bet in these calculations, original number here had 3 significant figures. Our end guy will have 3 significant figures. Again, since this is a product, that would also represent our theoretical yield. Any questions on any of those steps there? Again, you can see the same 4 steps going on. And just to show you here, I think they did it all in just one calculation. So here's that. If I didn't write over it, hopefully not. Again, you could just do it all in one kind of big calculation, perfectly fine to do that way. And you can see, obviously, you get the same answer. So whichever way you want to do it is perfectly fine. Again, if you go step by step, just watch the rounding until sort of the end. Any questions on where I got any of those numbers, how we did any of those parts? Okay, so let's try a couple more here just to make sure. All right, go with this one here. What is the maximum amount of HCl in grams that can be produced from 20 grams of PCl3? So phosphorus is 3097. Hydrogen is 1.008. And oxygen is 16 here. All right, take a few minutes here and see what you come up with. So let's take a look and see how we're progressing here. So again, always just follow the same steps. So clearly, again, I don't see any numbers here in our equations, so it's really not balanced. So I believe if you lay up a 3 there and perhaps a 3 there as well, that should balance it up, I think. So we got 6 hydrogens on each side, 1 phosphorus, and 3 oxygens on each side, and 3 chlorines on each side, so we're good. Next thing is to take whatever they gave us, which in this case is 20 grams of our PCl3 and convert it into moles. And we do need to do that since it's in grams. So going here for our PCl3, we have 3097 plus 3 times 3545. And that looks like it gives us something like 137.3 grams per mole, which would be our molar mass. So we're just going to divide by that there, 137.3 grams per mole of our PCl3. Grams are going to cancel each other out. Again, if you want to do it all in one step, you can, but in case you did get an answer, you should be looking at something like 0.1456 moles of PCl3 at this point. That brings us really to the stoichiometry part. So obviously they gave us PCl3. We are looking for HCl. And again, from the equation, we can see for every 1 mole of PCl3, we get out 3 moles of HCl. That's going to give us our conversion factor that we need. Here we want to get rid of our PCl3, so it should go on the bottom, so it gets rid of it. And up on top should go our 3 moles of HCl. Again, that's going to be the stoichiometry part, step number 3 there. That's going to get rid of it. I'll put the answer over here, and we will end up with 0.4369 moles of HCl. Again, at this point, we're looking for grams, so that is going to require us to do the 4th step. Also a reminder that we have now converted to HCl. So for the molar mass, we want to make sure that we add together our HCl. So our HCl is going to be 1.008 for our hydrogen, plus our 3545 for our chlorine, going to get us maybe a 3545 plus 1.08. 3646 looks like. So again, we're going to use that to finish this up, 3646 grams per mole of HCl from the periodic table, step number 4. And we will end up with their 0.4369. Probably something like 15.9 grams of HCl. Again, here going with 3 significant figures based off of our original number here, which has 3 sig figs. And again, that would be considered our theoretical yield of HCl in this particular case. Any questions on any of those steps there? All right, let's take a look at one more here. How many grams of steam, which is H2O, must react with 375 grams of iron 3 oxide? So again, hydrogen 1.008, oxygen 16. Iron is 5585. I think that's by this time, I think. All right, take a couple minutes, see what you come up with. Okay, so let's take a look here. So again, same sort of steps. In this particular case, I do see coefficients, so I'm going to be pretty confident that it is balanced. You can always double check, but it does look like it is balanced here. So that means we're going to take what they gave us, which was 375 grams of Fe3O4, and we do want to convert it to moles. So again, we would use our periodic table to do that. And it looks like if you add up everything there for Fe3O4, you get something like 231.6 grams per mole. So we're going to use that as our conversion factor here, again, dividing by the grams. And that would get us here, if we do get answer 1.6195 moles of our Fe3O4. We then come to our stoichiometry part. Because we're interested in steam, which is water, we are interested in this guy, which is what they gave us. And again, in this case, we're actually going the opposite way, which is perfectly fine, as we talked about last time. And we want the relationship between this guy here. And that is still the same sort of relationship, 4 moles of water, going to give us 1 mole of Fe3O4. So we're going to use that for step number 3 here to convert it into what we're really looking for. So taking our number from previous step, we're going to do the stoichiometry part. Again, we want to get rid of the Fe3O4. So that's going to go on the bottom. Up on top will go our 4 moles of water. The moles of those guys will cancel each other out, and we will end up with something like 6.4781 moles of water at this point. Again, here we're not looking for moles, so we are looking for grams. So that is going to require us to do step number 4. And again, we have now converted into moles of water. We want to go to the periodic table. And as I talked about before, when we get the molar mass, regardless of the number that's there, because we already took it into account, it is just based off of the formula. So the molar mass for water is 18.02 grams per mole. 2 hydrogens at like 1 gram and 1 oxygen at 16. So that's what we want to use here, the 18.02 grams per mole of water. Moles are going to cancel. And we will end up with about 117 grams of water in this case. Again, 3 sig figs off of our 3 sig figs from our original number here. Everything else pretty much a conversion factor. You don't have to worry about it. And we get this. This, by the way, again, is not a yield. This is not a theoretical yield. This is a reactant. So yields are only on the product side. So we wouldn't classify this as a theoretical yield. What we just got here, it's basically a reactant. So this is a good example, as we talked about last time. You could do stoichiometry going whichever way you want to go. We could go from reactants to products like we did previous. You go products back to reactants, and you could even stay on the same side of the reaction. So again, you could do it between the 2 reactants, these type of calculations. You could also do it between these 2 products as well. You don't even necessarily have to cross over the arrow doing our stoichiometry here. Any questions on basic stoichiometry problems? Hopefully you can start seeing a pattern here that it is really those same 4 steps along the way. Okay, so what we'll do, we'll skip this one in case you want to do it yourself. The correct answer here is A, in case you want to do it later or something like that for more practice. The right answer is A, and we're going to continue on talking about a little bit more complicated sort of stoichiometry type problems. So that brings us to the idea of what is known as basically limiting reagents. And the idea of what's known basically as limiting reagents, some people call it limiting reactants, same idea. But limiting reagents is essentially the idea that really what happens when we do a chemical reaction is based on stoichiometry, there's always something that gets used up first. So there's always some reactant that pretty much kind of gets used up first and gets completely used up as a result of this chemical reaction. And that really is what is known as the limiting reagent. So the limiting reagent is really the reagent, which is always going to be a reactant on the left-hand side of the arrow. It's the one that gets used up first. And then we also have one that we have plenty of. So we've got plenty of the other reagent. And that is what is known as the excess reagent. And why these are important is just a basic sort of example here. If we look at this reaction, in order for this to basically produce NH3, we need some nitrogen and we need some hydrogen. If one of those things get used up, so at some point, let's just say we ran out of nitrogen in this case, we would have no way to make any more NH3 units because we basically have lacked hydrogen. Or, I'm sorry, lacked nitrogen in this particular example. And the reason that's important is it's always the limiting reagent that determines how much product you can make. So a very simple sort of example again is we take A plus B to make AB. As soon as you run out of one of those guys first, so again, we just say we ran out of A, there's no possible way you can basically make any more product. So when we're trying to determine, for example, how much product we're going to make, we always want to look at it in terms of the limiting reagent. It's always the important one to look at. How do you know it's a limiting reagent problem and not sort of a basic stoichiometry problem like we've been talking about? The very key way to basically determine that it's a limiting reagent problem is you're given enough information to calculate the moles of all your reactants. So if you think about some of the problems that we just did, we pretty much were only given one piece of information. And that's not enough to obviously calculate the moles of everybody. But if you're given basically the starting amounts of both reactants and you're able to get the moles of both reactants, that is usually a pretty big indication that we're dealing with a limiting reagent problem, which means somewhere along the way, you need to basically figure out which one is the limiting reagent so you can figure out how much product would be made. Now, there's many different ways that you can sort of figure out limiting reagent type problems. So we'll go, I think, with the way that they do it in the book, but there's many sort of different ways you could kind of do these problems. But we'll just kind of focus on, I guess, how they do it in the book. So again, here, just sort of an example as we talked about, at some point here, we see in this case that the H2 was actually the limiting reagent here. The H2, as we can see, just picture-wise here, gets used up to make our products. We also can see that the excess reagent in this case was actually the N2. We could also, and a very common question is how much excess reagents left over when it's all said and done. And we could count, we have 2 of these guys left over when it's all said and done. We obviously have none of the H2 guys still there when it's all said and done. So again, in that particular example, again, the H2 was the limiting reagent. It gets used up. That's going to prevent us from forming any more product in that particular case. So same idea here. If we look at this reaction, we kind of just look at our pictures to try to determine it. We have some CH4 molecules. We also have some water molecules that are being formed. And when we look at this here, we see that we do have the water molecules getting used up first, which is our H2O. These guys get used up. And that means that it's the limiting reagent. Our methane would be our excess reagent in this particular case. Again, we have some of those guys left over when it's all said and done. All right, so let's talk about calculation-wise as to how you could do it. So this is one approach to do limiting reagent problems, and I think it's the way the book does it. So we'll kind of do it this way, I guess. But basically, it's really the same 4 steps. So you're going to write the equation, make sure it's balanced. You're going to, in this case, see that you're given the starting amounts of both reactants. So you're going to convert both of those reactants into moles. And then you're pretty much going to do 2 separate calculations. One calculation taking one of the reactants to the products and figuring out how much it made. The other calculation would be taking the other reactant to the product and figuring out how much it made from that. The one that makes the least amount of product is your limiting reagent and also your theoretical yield. So you basically just do 2 separate stoichiometry calculations like we've been doing, and whichever one ends up producing the least amount of product is your limiting reagent. By default, the other guy would be your excess reagent, and that would also be your theoretical yield, basically what you came up with. So let's take a look at one here and see what we're coming up with. Again, a reminder that you always want to do this. You want to do this calculation. Sometimes people think, well, I'm starting with 5 grams of A and like 2 grams of B. Well, I'm starting with 2 grams of B. That's got to be the limiting reagent because it's the smallest amount. And that's not always the case, because it's really based on the stoichiometry, the mole-to-mole relationship. So you can't always determine, oh, this is starting with less grams, so this is going to be our limiting reagent. You do have to do the calculation. Because of the stoichiometry, it may actually be something different than that. So sometimes people just look at it and go, I know for sure it's the smallest, it's going to be it, and it's not going to be that always. So you definitely got to figure it out by doing the calculation here. So now let's take a look at one here and see. So how many grams of NH3 would be produced from the mixture of 3 grams of nitrogen and hydrogen gas in this case? So a couple of things. The first thing they tell us is we have 3 grams of hydrogen, and we're going to mix it with 3 grams of nitrogen. So right off the bat, that is both of these guys in terms of our reactants. We have enough information to get the moles of both of those. So right off the bat, that tells us this is a limiting reagent problem. Because of that, we're given both of the starting material here. We're going to approach it the same way. We're going to balance the equation. It's not balanced. So again, here we need a 2 there, and we also need a 3 there to balance it. Now, we're going to kind of start it the same way. So what we're going to do is convert both of these grams into moles. So really step number 2, we could kind of do the same deal. We're going to take 3 grams of hydrogen. We're going to go to the periodic table and convert hydrogen's molar mass. So that is 2 times 1.008. That's going to give us 2.016 grams per mole of H2. And that will get us 3 divided by 2.016. Going to give us 1.49 moles of hydrogen. We're also going to convert our nitrogen into grams. So we're going to go 3 grams of nitrogen. Also going to go to the periodic table, get the molar mass of nitrogen. That is 2 times 1401. That's 2802 grams per mole. So we're going to divide 3 divided by 28.02, going to give us 0.107 moles of nitrogen. So first 2 steps, pretty much similar to what we did before. Step number 3, we're just going to kind of do step number 3 and 4 together here for each of them. So we're going to start with our H2. So we have 1.42 moles of H2. We're now going to pretty much figure out how many grams of NH3 it will produce. So from the equation, we see that for every 1 mole, H2 first. So for every 3 moles of H2, there is 2 moles of NH3. So that's what we're going to do next. So for every 3 moles of H2. There is 2 moles of NH3. And again, if you got an answer at this point, you are looking at 0.9467 moles of NH3. We then can convert that into grams, which is step number 4. We need the molar mass of NH3, so that's 14 plus 3 times 1.008 for our hydrogen. That is 1703 grams per mole of NH3. And that would get us 16.1 grams of NH3. So what that number represents is how many grams we would produce from H2 in this case. Now we want to determine which one's the limiting reagent, so we're just going to gear back up and start again, and we're going to calculate how many grams we would produce if we started with the nitrogen. So we're going to do to the nitrogen now. And now we need the relationship between nitrogen and NH3, and that is 1 mole of N2 is 2 moles of NH3. So doing our same step 3 and 4 calculation here, 1 mole of N2 is 2 moles of NH3. And that would get us, starting with nitrogen here, 0.214 moles of NH3. We then could use the same molar mass of NH3 as we did above, which is 1703 grams per mole. And that would get us 0.214, and 0.214 times the right number there, 1703, gives us something like 3.64 grams of NH3 would be produced from the nitrogen. First off, any questions on those calculations? So we're basically just doing 2 separate calculations, one from each of the reactants to the product we're interested in to help us determine which one's the limiting reagent. And if we do that, what we see is this one right here is the smallest. That is the smallest. And that means that this right here is our theoretical yield. So really, this is not our limiting reagent. That also tells us, because that's our theoretical yield from our nitrogen, that our nitrogen in this case is our limiting reagent. That would mean that our H2 would be our excess reagent. Any questions on that calculation there? Now, another kind of thing that you're sometimes asked for is, can we figure out how much of our excess reagent is left over? And we can do that. So if we wanted to figure out in this particular example how much our excess reagent was left over, we would have to do another calculation here. So let me just kind of back up here. I can be part of this page here. And in this particular case, we have 0.107 moles of nitrogen we're starting with, and we have 1.49 moles of hydrogen. So we have 0.107 moles of hydrogen we began with, and we have 1.49 moles of nitrogen. This is how much we started with. So what we just figured out is that in this particular case, this is our limiting reagent, and this is our excess reagent based on our calculation. So if we want to know how much of our excess reagent is left over, we would need to do a little calculation between our nitrogen and our hydrogen here. So if you remember, this was our equation here that we were dealing with. So since we already determined that this nitrogen is our limiting reagent, we want to figure out how much of our H2 we need to put in there to completely use it up. So it's just a simple little calculation. We would start with our limiting reagent, which is 1.49 moles of N2. We would do a mole-to-mole relationship between the nitrogen and the hydrogen, and that is a 1 mole of nitrogen gives us 3 moles of H2. And we would just do a little calculation here. 1 mole of nitrogen, 3 moles of H2. That's going to tell us that we will end up with what we got here. Hang on one sec here. The right numbers. Make sure. Doesn't seem right. Hang on here. I think I put the wrong numbers down here. 1.49. Yeah, I have those numbers backwards, so that's not so good. Let's try that again. So this is actually our nitrogen, right? And that is our hydrogen. So I think that's better. So switch that around. I guess it helps if you start with the right numbers there. So this is 1.4 moles. This is our limiting reagent. Take 2, sorry about that. 0.107 moles of our nitrogen, right, is what we have. And same relationship, 1 mole of nitrogen, 3 moles of H2. That should come out a little bit better there. There we go. 0.321 moles of H2 is needed in this particular case. And that is how much H2 is needed. This is how much we started with of the H2. And if we just subtract those two numbers, that will tell us that we have about 1.17 moles of H2 left over. And if we want to know how many grams that would be, we obviously could times it by 2.01, and that gives us about 2.36 grams of H2 that's left over. Again, we started with 3 grams of H2, so we used just a little bit of it in this particular reaction. So if you want to figure out how much of your excess reagents left over, you just need to do a simple little calculation between the two reactants and subtract off how much you needed to use from how much you started with, and don't screw up by mixing up the numbers like I did. That would probably be better. Any questions on that part of it there? Okay, so let's try another one here. So which one here? Let's go with this one. How many grams of what we got here? Barium sulfate can be produced when barium nitrate reacts with sodium sulfate. So here, let me just throw out some equations here, right? This is barium nitrate reacting with sodium sulfate. Going to be a double displacement reaction, going to give you some barium sulfate and some sodium nitrate. All right, continue at that point. By the way, this is solid, this is aqueous, in that particular case. All right, so barium is, where are we at there? 137.3. Nitrogen 1401. Oxygen 16, and sodium 2299. I think that's everybody. All right, see what you come up with. We want to know how many grams of barium sulfate here we would produce. See what you come up with. Okay, so since we're getting to the end here, let's take a look and see how we're doing. So again, we know this is a limiting reagent problem because we're starting with 2.45 grams of basically both reactants. So again, that's really the key to know that, this is a limiting reagent problem. Again, you're given enough information to figure out the moles of each of the reactants. Again, if you're not given that type of information, then it's not a limiting reactant problem, sort of a basic problem like we did before. We obviously, as we did here, have everything in words. We want to make sure, again, we get the right formulas down. This is a double displacement reaction, precipitation reaction like we talked about. We need to make sure it's balanced. So it looks like perhaps we just need a 2 there. It gives us 2 sodiums, 2 nitrates, a barium, and a sulfate, and it will be balanced. We then want to basically convert each of these guys into moles. So we're going to take 2.45 grams of our barium nitrate, and we're going to use the molar mass from the periodic table there to convert it. And it looks like if we do that, 137.2 for our barium, plus there are 2 nitrogens times 1401, plus there are 6 oxygens, each at 16, gives us something like 261.2 grams per mole of our barium nitrate. And that ends up giving us 0.00, we'll call it 9379. I'll take it to a couple digits here of barium nitrate. We also want to convert our sodium sulfate into that moles as well. So 2.54 grams of Na2SO4. Again, here from the periodic table, we got 2 sodiums at 2299, plus a sulfate at 3207, plus 4 oxygens at 16 each. Looks like 142.1. And that's going to give us a starting moles of 0.01724 moles of our sodium sulfate. Any questions up to that point? At this point, we're again just going to do 2 separate calculations to figure out how much product each of them produce. And in this case, since there are multiple products, we're interested here in our barium sulfate. So we're just going to do 2 individual calculations to figure out how much barium sulfate each of those will produce. So if we start with our barium nitrate, we had 0.009379 moles of barium nitrate. Going to the equation, we can see that it is a 1-to-1 relationship, so that makes it pretty easy. 1 mole of barium sulfate to 1 mole of barium nitrate. And again, that's the stoichiometry part. That's going to cancel out our barium nitrate and going to leave us 0.009379 moles of barium sulfate. We then want the molar mass of barium sulfate, so that is 137.2 plus 1 sulfur at 3207 plus 4 oxygens at 16 gives us 233.3, so taking 0.009379 moles of barium sulfate times in by the molar mass of barium sulfate, which is 233.3 grams per mole, gives us roughly 2.19 grams of barium sulfate would be produced from the barium nitrate. Now, we don't know if that's our theoretical yield or not until we do our second calculation. So we're going to do our second calculation starting with our sodium sulfate. And we're going to go to the equation, and we see between sodium sulfate and barium sulfate also still a 1-to-1 relationship. So 1 mole of sodium sulfate, 1 mole of barium sulfate. going to give us 0.01724 moles of barium sulfate. We then will multiply that by our molar mass. And it's the same molar mass for barium sulfate as we used above. Squeeze it in here to 33.3 grams per mole. And we end up with 233.3 times 0.01724, going to give us 4.02 grams of barium sulfate that would be produced from this sodium sulfate. That means that this guy actually is going to be our theoretical yield. This one here gave us a larger number. So this would be our theoretical yield. That also means that in this particular reaction, our barium nitrate was our limiting reagent and our sodium sulfate was our excess reagent. Any questions on that calculation there? Yeah. So we'll stop there for now. We'll take a little break. We'll pick back up in lab. We're going to finish a few more samples of these or examples of these, again, because it relates to the lab we are doing today. So we are going to do experiment 15 after we're done going through a couple more examples here, especially about percent yield, which is kind of where we're at next, and that's in the experiment.